Hello, we are Luna, Kaya and Stefan, and in this video you will learn about phase changes and how to analyze them. In particular, we will introduce you to the three concepts phase response curves, phase transition curves and Poincaré phase maps. Synchronization is the dynamical process by which two or more oscillators adjust their rhythms due to their interaction. In other words, elements which are coupled in a dynamical system tend to synchronize their behavior spontaneously and without any leader. This phenomenon can be seen in many systems. A commonly used example are the metronomes, which are connected to each other through a bar and slowly adjust their rhythms so that they tick synchronously. In this video, we are more interested in the synchronization of firing neurons, which show the same behavior. To analyze the synchronization of neurons, we can use phase response curves, phase transition curves, and Poincaré phase maps. As the term phase occurs in all of these three methods, we should have a closer look at what this actually means. Here you can see the firing pattern of a single neuron. As its pattern repeats periodically, we can call it an oscillator. Now, if we imagine the graph as a road that we can drive along, then we notice that the more the membrane potential changes in 1 unit of time, the faster we would have to drive. This can also be represented in a limit cycle. But what we actually want is a representation of this period where the speed with which we, so to speak, drive along the road stays constant all the time. So now we don't try to drive different distances in the same amount of time, but we finish the complete period with the exact same speed. And we can do that by mapping the period onto a circle, so that the beginning of the phase corresponds to 0 degrees and the end corresponds to 360 degrees, or 2 pi. This representation can help us determine the relative speed change after a perturbation. Now let's move on to the first method for analyzing phase changes, namely phase response curves. A phase response curve describes the magnitude and direction of phase changes after perturbing an oscillatory system. In the example of neurons, that would mean that we can analyze how the neuron will change its firing pattern after a pulse at different moments in the oscillation. In order to obtain a phase response curve from a neuron, one would record its normal activity, which is the black line in the first plot. Then, one would apply identical pulses at different moments in the period and each time record the firing pattern. In the plot, you can see that the pulse, which is indicated as a blue arrow, has only a small effect on the firing pattern, which is the blue line, whereas the pulse which perturbates the neuron a few milliseconds later, at about half of the period time, has a stronger effect. To plot the PRC, one would calculate the difference between the unperturbed and the perturbed neuron and plot this result against the initial phase. In the second plot, you can see how the PRC typically looks like for neurons. Looking at it, you can determine the amount of phase difference that a pulse produces depending on the moment it was induced. On top of that, the PRC tells us whether the pulse will result in an advance or a decay of the phase. We will have a closer look on the next slide, where I will talk about two different types of neurons, class 1 and class 2 neurons. If the phase difference, which again corresponds to the y-axis of the PRC, is positive, then there is a phase advance, or in other words, a shorter period than without the pulse, whereas if the difference is negative, there is a phase delay, meaning a longer period. In class 1 neurons, no matter at which moment the perturbation happens, the phase will always be advanced or always be delayed. This is called monotonic. In class 2 neurons, this is different. As you can see in the lower sketch, there are moments in the phase for which the perturbation results in an advance and other moments where it will result in a delay of the phase. Because of this biphasic behavior, these neurons have an advantage in terms of synchronization compared to class 1 neurons. Whereas class 1 neurons can only synchronize by becoming faster, class 2 neurons can either fire faster or slower and thus can reach synchrony more easily than class 1 neurons.
Now let's continue with phase transition curves. They are an alternative to the phase response curves, but instead of explaining the phase change, they give the result after the perturbation of the system. If we take a look at the formula on the right, we can see that the PTC of a phase is actually the sum of the initial phase and the phase change that we can get from the PRC modulo the period length of the system. The PTC is therefore equal to the new phase of the system. We can plot it by plotting the new phase against the initial phase, as can be seen in the picture, with the new phase on the y and the old phase on the x-axis. Let's look at these two examples. The PTC is always compared to the diagonal line, here marked in red. If the curve is perfectly on the diagonal line, there is no effect of the perturbation. Anything below the diagonal means the effect is delayed, everything above the effect is speeding up. So what are the different usages of PRC and PTC? In general, we can say that they can be used simultaneously. The PRC is, however, most often used when studying the principal behavior of a system, so if we want to know how much it is speeding up or slowing down. And with the PTC, it can be easier to look at the effective phase that a system is in.
So far we only looked at the effect of single impulses on the phase of a system. We will change this now when looking at Poincaré phase maps. First, let's start with an intuition. The general idea is that a constant drive is applied to a system, for example multiple input pulses with a constant time delay. The question that we then pose is, do driving and driven systems synchronize their phase behavior? Let's have a look at this exemplary signal here and the impulses displayed at the bottom. We will come back to it in a bit. As we can see in the top row, the phase delay of the system that was induced due to the impulse changes over time. The question is, does this delay behave in an ordered fashion over time? For example, does it go towards a fixed value? Let's continue with a bit more in-depth look. We already saw phase response curves, so we can construct the phase now for multiple impulses similarly by calculating that the PRC offset is added for each impulse with a value depending on that impulse, as well as a phase offset depending on the position within the period between the pulses. In total, the current phase corresponding to the current impulse can be expressed as the last phase value corresponding to the previous impulse plus the phase response offset of the last phase value plus the phase offset depending on the position within the period between the pulses. The entire expression is taken modulo the period length of the system. How do we now get to the phase maps? Let's consider again the signal that we saw earlier. We can plot the phase offsets for each impulse individually, as shown in the right upper picture. Remember, what we're interested in is a statement about whether synchrony happens or not. In this plot already, it becomes obvious that the phase offset tends to anneal at a constant level. It could be assumed that the driving and driven systems synchronize. It's also possible to display the information in a different way. Now the Poincaré phase maps come into play. To generate them, let's first consider what is plotted here. On the x-axis we have the phase corresponding to the last impulse, and on the y-axis the phase corresponding to the then following impulse. The diagonal indicates that there is no change in phase, either shifted forward or backward, between previous and next impulse. Now in the plot, the impulses' phases are drawn specifically in a way that always pairs are considered. So for example, for the first point, the first impulse's phase is considered as x-coordinate and the second impulse's phase is considered the y-coordinate. Similarly, all point pairs are drawn in and connected by arrows indicating the direction. Depending on their behavior, the stability of the system can be determined. Let's consider the diagonal again. It represents the fixed points, so points where x and y are equal. If in a Poincaré phase map the drawn in arrows gravitate towards and end on the diagonal, the system is stable. Since there's no change of phase between the impulses anymore, then driving and driven systems synchronized. If the arrows go away from the diagonal, the system is unstable. Let's look at some examples. Here on the left there are two examples of stable fixed points and thus synchronizing systems, and on the right there are two examples of unstable fixed points and thus not synchronizing systems. For each of the four cases, the left subplot shows the Poincaré phase map and the right plot shows the progression of the phase per impulse. In the case of the two stable fixed point examples, it's immediately visible that the phases tend to a stable value in the right subplots. In the upper case, the values near from above the stable value, and in the bottom case, the values oscillate around the stable value with some value below and some above it. Those two behaviors become obvious also in the Poincaré map, where in the lower case, the lines that are used to draw the individual points form a spiral-like structure, while it's a staircase-like descending structure in the upper case. In both cases, a curve that goes through the individual points directly can be drawn. At its intersection with the diagonal, it shows an equilibrium of the system. For the stable fixed points, these are stable equilibria. Looking at the right side, two examples of unstable fixed points are shown. Here in the right subplots, the faces diverge with increasing number of impulses, and in the Poincaré maps, the lines that are drawn between the individual points tend away from the equilibrium, either in the staircase ascending fashion or in a spiral that gets ever bigger. In both cases, the equilibrium is thus an unstable equilibrium.
To sum it up, the PRC describes the phase change of a system after a perturbation. They can be used to study its principal behavior. The PTC, on the other hand, describe the effect after the perturbation. They can be easier to use when looking at the effective phase a system is in. Poincaré phase maps not only look at a single impulse, but a constant drive that is applied to a system. They are used to study the phase change behavior and can be used to describe the synchronization of a system. We hope you enjoyed our video and thank you for watching.